Hey 13 diplomas, welcome back to 18.2. It's part C, calculation time. So we're just going to jump straight into it. So the first thing to talk about is the fact that we have to make a really big assumption with all of our calculations here. And essentially what all of this is saying is that whatever your original weak acid concentration is, we're going to use that concentration as being the equilibrium concentration. Reason being is that if a weak acid dissociates into its ions, so little of it dissociates. So if I've made up this figure, but if the figure's 0.001, then that's going to make very little difference if we subtracted it off our HA to get our equilibrium concentration. So therefore, we're just going to say that the concentration of our weak acid will be the concentration at equilibrium. And remember, when we do any calculations involving equilibrium, it has to be equilibrium concentrations that we use. Okay team, so here is our blank template of how we do these problems. So HA stands for any weak acid. When you react it with water, you produce H3O plus and A minus. These two ions are produced in a 1-to-1 ratio. So when we write our Ka, products divided by reactants, you can see here that here's our products divided by reactants and no water. And what you can see is that from this equation up here, H3O plus and A minus have exactly the same concentration because they're produced in a 1-to-1 ratio. So that means we can minimize the number of unknowns in our equation by making them this, because they are the same, we just do H3O plus squared. We keep H3O plus and not A minus because we're always trying to solve for H3O plus for pH. Okay, so the next thing we do is rearrange. So we times the HA over by the Ka here, and you get H3O plus squared. And then we just square root that Ka times the concentration of the acid, and that'll tell us the H3O plus concentration. So what value we use for the acid here is actually the initial concentration of our weak acid, because remember we're saying that so little dissociates that it really doesn't make much of a difference to that concentration. We then negative log our H3O plus, and that gives us our answer. So let's look at an example together, guys, so we can actually make sure that we can do this. So calculate the pH of a 0.2 mole solution of methanoic acid, and they've given a Ka. You'll always be given the Ka. You have to start always by doing an equation. So methanoic acid plus H2O, so every problem should have an equation, goes to methanoate, HCOO minus plus H3O plus. Step 2 is to write a Ka. So Ka equals HCOO minus times H3O plus divided by the acid. Remember, we're excluding water. Okay, so from here we're just going to rearrange, and we first of all know that the H3O plus and the COO minus, HCOO minus are in a 1-to-1 ratio, so we can minimize our unknowns just by making that H3O plus squared divided by HCOOH. Okay, we can times HCOH to the Ka, and therefore our H3O plus concentration is going to be the square root of the Ka times the concentration of our acid. The big assumption we make is that so little of our weak acid dissociates, so that at equilibrium its concentration won't have changed much. So we can just plug in these values. So 1.82 times 10 to the negative 4 times the concentration of your acid, 0.2, and if you square root it, that'll give you your H3O plus. I'm just going to do this now on the calculator as well. I hope you guys can get out your calculators and do that too. And hopefully we all get the same answer, which should be 6.03 times 10 to the negative 3 moles per litre. So that has a concentration because it's the concentration of hydronium. And then the final step to this problem is to negative log your answer there. And if you negative log the answer, you'll end up with a pH of 2.22. So I hope that makes sense. And let me know if you have any questions. Okay, and this is the working again. Okay, example 2, calculate the pH of a 0.01 mole per litre solution of ammonium. Now remember, ammonium is the conjugate acid of the weak base NH3, and it's weakly acidic. So we can write the equation NH4 plus aqueous plus H2O, equilibrium arrows forms NH3 aqueous plus H3O plus, and we can do a Ka expression. So Ka equals NH3 H3O plus divided by NH4 plus. We can see from our equation these are produced in a 1-to-1 ratio, and so to minimize our unknowns we're going to make Ka equal H3O plus squared divided by NH4 plus. We then rearrange, and so the concentration of H3O plus, is going to be the square root of your Ka times the concentration of your acid. So we're going to use the same concentration of our weak acid at equilibrium because very little dissociates. It's not going to affect its concentration very much. And, that should be a 0.1. And when you've got your answer, that'll give you H3O plus, which you then negative log. And I'm going to flip to the next slide because the answer's already there for us. And so when you do that, here's the working, you get 2.4 times 10 to the negative 6 moles per litre. If you negative log that, the answer's 5.62. Okay, team, so here are 2 more problems. I'd really like you to pause the screen. Now, for some of you, you should best practice do the equation each time and the Ka, but some of you will be starting to realise that you can actually jump straight to this point. So H3O plus equals the square root of your Ka times the concentration of your acid, and so therefore the answer just becomes 1.74 times 10 to the negative 5 times your concentration, which is 0.453, and so it starts to become a lot quicker, and so when you do that, I'm just doing it on my calculator now, you should get an answer of 2.8 times 10 to the negative 3, and if you negative log that answer, you end up with a pH of 2.55. Okay, so you can start getting a lot quicker when you start to see the pattern. So again, methanoic acid, so it'll be H3O plus equals the square root of the Ka times the concentration of the acid, which equals the square root of 1.82 times 10 to the negative 4 times 0.275. Okay, and if we plug that into our calculators, and you need to be able to make sure you can put these in your calculators, you guys are not that good at that, you get 7.07 times 10 to the negative 3, and if you negative log your answer to get a pH, don't know what I just pressed, the answer will be on the next slide, sorry, I just pressed something on my calculator. Oh, no, it wasn't. Okay, so we will just finish that off. So if you negative log 7.07 exponent negative 3, you get 2.15. Okay, so the pH equals 2.15. If you've got any questions, let me know, but that's essentially how you calculate the pH of a weak acid. So the key thing is that the expression that you really need to be able to get to is the fact that H3O plus equals the square root of your Ka times the concentration of your acid. And if you can remember that, happy days. So how do you calculate the pH for a weak base? Now you'll see here that I've put using the Ka method. This is the method that I absolutely prefer because we're about to lead on to a section on buffers where you have to use this method. There is an alternative method which I'll show you, but this method is what I prefer. To use the Ka method, we need to convert our base into acid essentially. And so what we do is here's base, reacting with water and it accepts a proton and you get OH minus. We're going to do a second reaction with this conjugate acid with water so that we can produce hydronium ions. Okay, so we make up the second reaction even though the top reaction is what we know is happening, just so we can get hydronium ions to work with. So when you do products divided by reactants, you'll see I've put Ka of the BH, you end up with this expression. Now, what you can see from this first reaction is the same as from our weak acid. The BH plus concentration and OH minus concentration are the same, okay, because they're produced in a 1-to-1 ratio. So therefore, if these have got the same concentration, that means that instead of having this BH plus here, we could have OH minus here. And we know that an expression that we already know off by heart that stands for OH minus is Kw divided by H3O plus. So what we're actually going to do is substitute this instead of this BH, and that means that we're actually minimizing our numbers of our known because now we've put H3O plus in there, which we've already got, and Kw is a known. So now our expression looks like this. And so if you don't know how to rearrange this stuff, you don't really need to. You just need to realize that it ends up being this here. So that H3O plus ends up being the square root of your Ks. I always say the square root of your Ks, so Ka times Kw divided by the concentration of your base. And just like the weak acid, the concentration of the base that we use is the original concentration of the weak base. Okay, and once you've got your H3O plus, then you can just plug it into your pH here. So let's do an example. So the example, calculate the pH of 0.2 solution of ammonia. So ammonia is a weak base. So we're going to do the equation first, best practice for the first few. Plus H2O, okay, goes to NH4 plus aqueous plus OH minus. Because we're doing the Ka method, we need to do a second equation, NH4 plus aqueous plus H2O goes to, equilibrium errors here, sorry team, goes to NH3 aqueous plus H3O plus. We can now do a Ka, so your Ka equals NH3 times H3O plus divided by NH4 plus. We know that NH4 plus and OH minus are in a one-to-one ratio, so their concentrations are equal. So we're going to actually replace the NH4 in our expression here for Kw divided by H3O plus, because we know that actually if this is the same as OH minus actually equals Kw divided by H3O plus, and it minimizes our unknowns. Now to rearrange this, H3O plus ends up equaling the square root of your Ka times your Kw divided by your concentration of your base. And I'm not going to go through how to rearrange it. You can do that on your own and see me later if you need to. So now we just plug in the values. So that equals the square root of your Ka. And this is the first time we're seeing something here, pKa. So this is something that I'm going to be teaching over the next couple of bits. And so I introduce it here. So pKa and Ka are a mathematical relationship simply to make a bigger number. So to go back from a pKa to a Ka, you go Ka equals 10 to the negative pKa, and you'll get your Ka that you are used to dealing with. So 10 to the negative 9.24 gives you a Ka of 5.75 times 10 to the negative 10. So if you were wanting to convert between a pKa and a Ka pKa equals negative log Ka, and that'll give you your pKa. So what's the point of doing a pKa? Well, writing out this big faffy long number is a pain in the butt sometimes, and we can't be bothered doing it the whole time. So that's why we do it, okay? So we use a pKa just because 9.24 is a lot nicer to use than 5.75 times 10 to the negative 10. Okay, so the Ka is, we'll be doing a lot of practice of that. 5.75 times 10 to the negative 10. We know that Kw is 1 times 10 to the negative 14. The concentration is the concentration of the base, which is 0.2. And when you plug that into your calculator, you'll get an H3O plus concentration, which we then negative log to give us the pH, and all the workings on the next slide. So you can see everything I've done there. Okay, so if we plug in all those values, you get an H3O plus of 5.36 times 10 to the negative 12. If you then negative log that, you get 11.3. So here's another example. So let's go through this now. It says calculate the pH of a solution of sodium ethanoate. Now sodium ethanoate is actually a salt, and we know that salts exist as solids, okay, and so that'll dissociate into CH3 COO minus plus Na plus, and we're really interested in this. Ethanoate ions are the conjugate base of ethanoic acid, and we know that conjugate bases of a weak acid are weakly basic. So what we can do from here is we actually know what this equation is going to end up being. We know that it's going to be, because it's a weak base reaction, it's going to be the square root of your Ka times your Kw divided by the concentration of your base. And you start getting really quick at this because it just has those two patterns. So 1 times 10 to the 1.74 times 10 to the negative 5 times 1 times 10 to the negative 14 divided by the concentration of your base, which is 0.4. And you can work out your H3O plus concentration and then negative log that to get your pH. And so the answer there for that is 6.6 times 10 to the negative 10. And if you negative log that, you get 9.18. And you can see all of the working here. But as I say, you'll get to the point where you actually can just jump to this because it's much easier. Okay, I'll see you soon for part D.